Hello grade 10s and welcome back to another video with me, Miss Martins. If you haven't subscribed yet, what are you waiting for? Please subscribe, give this video a thumbs up so I can give you a lot more content like this. Let's go. We're going through some physics questions again. And I put the paper that I'm going to be starting with on the screen. So we're doing physics, paper 1. Let's jump right into it with a multiple choice question. So this question says the EMF of a battery, we can see this is a electric circuits question, electricity question. The EMF of a battery is V. Now, what a nice thing to do when doing a multiple choice questions is to eliminate the options that are clearly wrong. So it says the force exerted by the battery per unit charge. That's definitely wrong. I know that's definitely wrong, so I'm going to cross that out. Here they speak about energy. And here they speak about energy. I know that EMF is related to energy. I'm going to explain why now. So it's one of those. Or potential difference across the terminals of the battery when delivering current. Now, EMF is basically voltage or potential difference, okay, of a battery. But here it says potential difference across the terminals of a battery. So you might think that that is correct. But you see it says here when delivering current. That's completely wrong. The EMF, so if I have to draw a quick circuit for you guys, the EMF, let's say there's a resistor there, and I attach a voltmeter, which reads potential difference across the battery. That voltmeter will read the EMF when and only when the switch is open and there's no current flowing. Okay, so I kind of messed this up. Like, I can't really draw this with an open switch, but imagine the switch was open. So open the switch. If the switch is open, and there's no current flowing, so open switch, no current, then the voltmeter across the battery will read the EMF only when there's no current and the switch is open. So this is completely wrong. Right, so if that statement said potential difference across the terminals of the battery when the switch is open or when there's no current, then it would be correct. Now, EMF, as I mentioned, is potential difference of voltage. And if you look at this formula for voltage, this is on your formula sheet. If you look at that formula for voltage, then we know V voltage potential difference. W, what is that? That is work or energy. Okay, work or energy. And Q is charge. And what is charge measured in? Charge is measured in coulombs. So look at this, see if this makes sense. Potential difference or EMF or voltage is equal to the energy supplied by the battery per, so per means divide, per coulomb charge. My answer is definitely A. It's not B because it's not energy supplied by the battery per unit current. This is per unit charge, not per unit current. I hope that makes sense. Okay, now before we get into more questions, I just wanted to remind you of series versus parallel circuits. In a series circuit, the current is the same everywhere throughout the circuit for the resistors that are in series. For resistors in parallel, the current splits. Voltage splits amongst resistors that are connected in series. But for resistors that are connected in parallel, voltage is the same. This is how we calculate total resistance if our resistors are connected in series. This is how we calculate effective resistance in parallel. Effective resistance in parallel. So if we take a look at these two circuits, this actually comes from a past paper. We can see that in circuit A, we've got two resistors that are connected in parallel. So you see that the voltmeter reading across the battery is 9 volts. Because I only have two resistors connected in parallel, it means that V2 will read 9 volts and V1 will also read 9 volts. Because voltage across resistors connected in parallel are the same and there's no other resistor in this series. If I was given total current, then I would know that the total current would travel through this part of the circuit and over here, and at this point there would be a split in current because these are resistors in parallel and current splits between resistors in parallel. If we look at circuit B, we can see that I only have two resistors here in series. There's no parallel combination over here. What that means is the 9 volts across the battery splits between the voltmeters that are connected or between the resistors connected in series. We can work out exactly what this voltmeter would read. If you're interested, it's V is equal to I times R. We know that the total current will flow through that resistor. Why? Because this resistor is connected in series. So the total current flows through here, 1.5 amperes, 1.5 amperes, 1.5 amperes, 1.5 amperes. Do you see? The total current, 1.5. There it is. The ammeter reads the total current. The total current flows through both resistors. So, in terms of working out what that voltage is on V1, if I'm working out V1, I'm going to put a little V1 over there. You use the current going through that resistor, which we said is the total current. It is 1,5. And I'm trying to work out the voltage across this resistor. So R that I must use, resistance, is just this resistor. So 1.5 times 2, and that is 3 volts. So V1 will measure 3 volts. What will V2 read? Can you tell me very quickly what V2 will read? Well, remember we said the voltage across the battery, the 9 volts, splits between resistors connected in series. So if 9 volts is the total voltage, the total potential difference, okay? Then 3 volts goes to V1, so then V2 will be 9 volts minus 3 volts. V2 will be 6 volts. But we could also work it out. Remember, we could go V is equal to I times R. The current flowing through this resistor will also be 1,5, the total current, but resistance in this case is 4. And if you go 1,5 times 4, you also get 6 volts. There we go. Pretty simple. So these are simple circuits because this only consists of parallel connections. This only consists of series connections. What you'll get in the exam is most likely a circuit that consists of both. But you need to understand the rules that apply for both cases. So here's a summary of what happens to current. Here's a summary of what happens to potential difference or voltage. So let's tackle our first past paper question. This one comes from that same paper that we did the multiple choice question from. So we've got study the circuit diagram below. They give me ammeters A1. Now you can see, let's just take a look at the circuit. We've got the battery. The total current will flow through the battery and the total current will flow through A1. Then we get to a split in the circuit. So if you had to put your finger, so if you're in the test, you're going to put your finger on the current, you're going to put your finger on it, you're going to go along. The total current will flow through all of this over here. Why? Because there hasn't been a split yet. Total current, total current, total current. But as soon as you reach the red dots, can you see there's a split in the circuit? So it means that this branch, the branch the 6 ohm is in, and this branch, the branch that the 3 ohm is in, those are in parallel. Okay, so the 6 ohm and the 3 ohm are in parallel. Okay, there's a split over there. And you can see here it joins up again, and then it's total current. And then this resistor over here, which they've labeled resistor R, this resistor is in series. So here we can see this is a combination circuit. Resistors in parallel plus a resistor in series. The other thing that I want to show you is that this A1 measures total current. How do I know? Because it's connected in series. It's not connected in a branch. Can you see that A2 and A3 are connected in the branches, which means that A2 and A3 does not measure total current. It measures the split current. So 3A, that is my total current. Can you see that the switch is closed over there? See the switch is closed. So this voltmeter V1 won't read the EMF. It'll read the terminal potential difference. That's what we call it. The terminal potential difference. So that is the reading across the battery when the switch is closed. Okay. And how it works is that V1, some of it will go to the parallel combination and the rest will go to this resistor. So we can see this resistor is 6 volts. So the rest of that terminal potential difference will go to the resistors in parallel, which is also 6 volts. So if 6 volts goes here, 6 volts goes here, it means that V1 must be 12 volts. And that's actually one of the first questions. So my first question is to define the term current strength. And current strength is the rate of flow of charge in a circuit. the rate of flow of charge. And I'm going to show you how you can remember that. The rate of flow of charge in a circuit. The way you can remember that is current. One of the formulas for current is Q divided by change in time. So rate, every time you see the word rate, I want you to think divide by time. So rate is dividing by time. Okay, cool. So rate divided by time, the formula, that makes sense. The rate of flow of charge, and we know that Q is charge. So a lot of the times in physics and in chemistry, you can look at the definition, the formulas, and it helps you get the definition. Okay, what is the reading on A3? So as we mentioned, A1 measures total current. So I'm going to write here total I. Remember, I is the symbol for current. So total I, that's the same thing as me saying total current. Then look at this. This is where the current splits. So some of the current goes down here, and that sum is 1 ampere. The rest of the current goes through this branch, which is A3's branch. So if 3 is the total current, and 1 ampere goes through here, then this must be 2 ampere. So when they want the reading on ammeter A3, they're basically asking what is the current through that branch? What is the current reading? So you can't just say 2, you have to say 2 ampere. You have to put the A, you have to put the unit, or you're going to get it wrong. Okay, what is the reading on V2? Now remember we discussed that for resistors connected in parallel, the voltage is the same. So now look at these two resistors. We've got this branch over here, which has the 6 ohm resistor, and this branch over here, which has the 3 ohm resistor. This branch will have the same voltmeter or voltage reading as this branch. Okay, so when the branches are connected in parallel, they have the same voltmeter readings. So the voltmeter reading across this resistor, or the voltage reading or the voltmeter reading across this branch is 6 volts. So because these are connected in parallel, V2 will also read 6 volts. Okay. Now that doesn't mean that overall here there's a voltage of 12 volts. No. This part of the circuit has a voltmeter reading or has a voltage or a potential difference of 6 volts. Okay. So therefore, the reading on voltmeter V1, remember V1 will read terminal potential difference or the total potential difference of the circuit. So V1 is basically equal to this voltage over here. So the voltage across R plus the voltage across the parallel combination. You don't have to write this. This is not a formula you have to write down, but I'm just trying to show you that the total voltage, this is the total voltage or the terminal potential difference, is equal to the voltage across this one, which is 6, plus the voltage across the parallel, which is also 6. So V1 will measure 12 volts. Okay, there we go, 12 volts. 2.3 asks us to calculate the effective resistance for the resistors connected in parallel. So those are these two resistors over here. Another word for effective resistance is basically the total or the overall resistance. Now, because they're connected in parallel, we know we are going to use this formula. 1 over Rp equals 1 over R1 plus 1 over R2. This is the formula that we use to calculate effective or total resistance for resistors connected in parallel. Now, 1 over Rp, that must stay over there. Rp is what we're looking for, resistance in parallel. R1 is all the resistors in this branch. And it's just the 6 ohm in this case. So it's 1 over 6 plus R2, all the resistors in this branch. So in this case, it's just 3 ohms, 1 over 3. Then we add those two together. Whether you get the LCDs, the common denominators, whether you use your calculator, it does not really matter. So 1 over Rp is equal to 3 over 6. And we don't want 1 over Rp. They asked me for the effective or total resistance of the resistors connected in parallel. So I want resistance in parallel. But look at what I have here. I have 1 over Rp. So what I have to do is I have to flip this over, get the reciprocal, flip it over. So basically we have Rp over 1 now. We flipped it over. Rp over 1, which is Rp. And because I flipped that side over, I have to flip this side over. So I'm going to have 6 over 3. And 6 over 3 is 2 ohms. So my resistance in parallel is 2 ohms. Again, you have to have your formula first. You have to have your blank formula. I was marking matric papers today and so many of them forgot their formula. If you forget your formula, you don't get that mark. It's a formula mark. Then this is called our substitution mark, and this is your answer mark. Okay, we have to do this in a separate step. So you first say 1 over RP is 3 over 6. Therefore, RP is 6 over 3, which is 2 ohms. Also, no unit, no mark. The next question says, if the total resistance of the circuit is 4 ohms, determine the resistance of R. So we want this. This is our unknown resistance. So remember, right now what we calculated was the effective resistance or the total resistance of this parallel combination. So this parallel combination or these parallel resistors had an overall resistance of 2 ohms. Now, if the total resistance is 4 ohms, how do we work out what this one is? Well, think about it like this. This resistance R is connected with the parallel resistors, so the parallel combination, and those two added together will give me the total resistance. So if the total is 4 and the resistance in parallel is 2, then that means that R must also be 2 ohms, because 4 minus 2 is 2 ohms. 2.5 wants us to calculate the quantity of charge. So you need to know that charge is Q. Charge is Q. That flows through the resistor R in 2 minutes. Now you have to go to your formula sheets, which I have shown in a previous video, and we know that I is equal to Q over T, or Q is equal to I multiplied by T. It's a rule in physics and chemistry to write the formulas as they appear on the formula sheet, and then you may rearrange them. So I'm looking for charge. So I'm looking for Q. That is my unknown. I want the charge that flows through resistor R, which is here, in 2 minutes. So you might be thinking, okay, cool, I'm looking for Q. I have time. Yay! But I don't have current. Well, remember, the total current will flow through this resistor. Why? Because remember, it's connected in series. The total current is 3 amperes. So I've got my current as 3 amperes. So I do have my current. My time is given as 2 minutes, but you need to remember that for this formula, it needs to be in seconds. So to convert to seconds, we times by 60. So I've got 120 seconds. So I have my time, I have my current, therefore I can work out Q. So as we do in physics and chemistry, we always write the blank formula first, then we sub in I is current, it is 3. Time must be in seconds, 120. So therefore my charge that flows through R is 360 coulomb. Now please, grade 10s, don't get confused between the quantity symbol and the unit. Q is basically like writing charge. So Q is like a shorthand way of saying charge, but C is the unit. It's what charge is measured in. This is coulombs. My next question is determine how much electrical work will be done by the battery in 2 minutes. Now, remember we discussed that electrical work is W, and we need to remember the formula V is equal to W over Q. Now, we need to think about if I have these other variables. So I'm looking for W, that's my unknown. I'm going to write it over here. W is my unknown. Do I have, now read the question carefully. They say the work done by the battery. Do I have V? Do I have the potential difference across the battery? Yes, I do. It's my reading on V1. And remember, we worked out the reading on V1 as being 12 volts. So I do have that reading, 12 volts. Do I have the charge? Do I have the charge? Now, remember in the previous question, We worked out the charge that flows through the resistor in 2 minutes. But think about what I use to work out charge that flows through the resistor. I use current, and now the current that flows through the resistor is the same as the current that flows through the battery. And the time in the previous question was 2 minutes, same thing as the time for this question. So therefore the charge that flows through the resistor is the same as the charge that flows through the battery. So that comes from the last question, 360 coulombs. I hope that makes sense, because remember, charge is current multiplied by time. The time is the same as the last question, 120 seconds. The current is the same as the last question, because the current that flows through the battery is the same as the current that flows through R. So therefore, we know voltage, we know charge. I'm looking for work. So we write our formula first, then we substitute in our variables. We know V, so V is 12, is equal to W. We are looking for W, and Q is 360. Now, how do I solve this? It's divide by 360 over here, so we need to take it over, and it's going to become times by 360. And there we go. The work done by the battery in 2 minutes will be 4,320 joules. Just remember, work is measured in joules.